So we've taken a look at these carbohydrate structures, and we've talked about these carbohydrates basically coming into two forms, R, S, or D and L. So R and S, typically if you're a chemist, D or L, typically if you're a biologist, but you can kind of see what's going on here, right? R or D as far as right hand rotation goes, and then S or L as far as left-hand notation goes. So it's up to you on whichever one you want to use. Again, we've said that before, and I'll keep saying it. Either one of these are proper, either one of these are correct. But we also talked about the idea that these carbohydrates could be positive and they could be negative. Now, positive and negative basically means the way they rotate light in a polarimeter. So they could rotate light right-handed, or they could rotate the light left-handed. Now, we could have R plus and R minus. We could have S plus and S minus. They're not related. We've said that before, and I'll keep saying that again over and over and over because I don't think that you can hear it enough. Okay, so this whole concept of positive and minus, with sugars, we said that when we make a sugar and put it in a polarimeter, we automatically get a rotation for it. And then if we allow that sugar to stay out in solution and allow it to come to equilibrium, these rings constantly open and close, the OH groups constantly switch back and forth between the alpha and the beta anomer, and we get some movement, some change that happens when we look at the optical activity of sugars, and that's why that goes on. So when you take a look at the Merck and you find a sugar, most of the time that optical activity is going to be given in a range, and that is why the range is presented, because it's all about, are you running it as soon as you make it, or are you running it 24 hours later after it comes to equilibrium? Okay, but there's more to the story than that. Of course, right? Of course there's always exceptions. So we need to take a look at maybe a simple sugar. And we'll take a look at C double bond O with a CH2 here, OH. And then here and here we'll put the OH groups on the right hand side. This is a structure that you should know. This is one that we told you to memorize. And this is the structure for your erythros. Okay, so if I take your erythros and I make a solution of it and I put it in a polarimeter, I will probably get some kind of optical activity. We see some chirality go on. We see that this can be labeled as a D or an L sugar. There's more than one chiral carbon here, so I'm going to see some optical activity that goes on. Sometimes, though, these sugars do not show any optical activity at all. But you've got to modify them in order for that to happen. So there is a point in time where you can make a sugar and undergo a reaction with that sugar and change it slightly, and then put it in a polarimeter and it not give you any optical activity at all. So we need to take a look at what that is. And the reason that this is so important is because this is part of one of your labs. If you take a look at the lab lineup, one of the labs is the structure of an unknown D-hexose. So we're going to give you a hexose. You don't know what it is. And you're going to basically have to determine what this hexose is. It could be an aldose, it could be a ketose. And if it is an aldose or a ketose, you're going to have to determine which one out of the lineup that it could be. And you do this by a number of tests, and one of those tests is a polarimeter. So yes, we do make a solution and we run it in the polarimeter and we get a range. The problem, though, is that these polarimeter reads, like we said before, some of them have very wide windows. So a polarimeter read alone might not be good enough to identify the hexose that you have. Another way that we could kind of determine this is undergo a reaction with it and change it and modify it in such a way to see if we can eliminate the optical activity. Okay, so what does that mean? Well, what you're looking for here is a plane of symmetry. And a plane of symmetry basically means that you can take the molecule and you can fold it in half. And if you can fold it in half and all the groups line up on top of each other, then you have a plane of symmetry. And if you have a plane of symmetry, you will see that these sugars do not have optical activity. Okay, so if I take the structure of your erythros, and if I fold it in half right here, right? So just imagine you draw it on a sheet of paper, imagine you cut out around it, and imagine you folding that sheet of paper in half. At that location, that is where the crease is. Well, you're going to see that these two H groups basically will stack on top of each other. You'll also see that these two OH groups basically stack on top of each other when you fold it. The difference here, however, is the C double bond OH and the CH2OH. Those do not overlap. They're not the same group, right? Okay, so because they're not in the same group, because they're not identical, when you fold it, the way that this structure is drawn, this one shows optical activity. Yeah, we folded it. Some of the actual groups folded on top of each other, but not every one of them. Now, if we could change this top piece into a CH2OH group, then, lo and behold, we get the same group on the top and the bottom. The hydrogens overlap, the OHs overlap, and we get this nice plane of symmetry that goes on. So if I can convert this structure, and instead of a C double bond OH up here, change that to a CH2OH group, and this still has the OH group to the left, or I mean to the right, and the third one still has the OH group to the right. Now when we fold this structure in half, everything overlaps. The H's line up with each other, the OH's line up with each other, and the CH2OH groups line up with each other when you do fold it over. So that is what we call a plane of symmetry. This sugar now, not really a sugar though really anymore, is it? It's not an aldose or a ketose. That functional group is gone. But that molecule has a plane of symmetry, and that molecule will not show optical activity when I put it in a polarimeter. So that is one of the ways that we can help identify, almost like a second test, what kind of sugar do I have. So if I know something about the structure, or if I don't know anything at all about the structure, and I basically take the C double bond O and I reduce it down to a CH2OH group, reduce the number of C to O bonds, and then put that into a polarimeter and it's optically inactive, I know a little bit about the structure of the sugar now. I know that this sugar has to be symmetrical, and that's exactly what you're going to do for the lab, at least in this course this semester. And you'll see some test questions and some quiz questions concerning this as well, because it is kind of important. It is a qualitative test that maybe we can do to kind of help identify an unknown if we have one. So the lab manual will go through and it will discuss this plane of symmetry a little bit more for you. How can we reduce, right? What is the special thing about reduction? Well, one of the ways that we reduced, if you go back and take a look at our reactions, is using sodium borohydride. So you can easily use NaBH4. That will reduce the C double bond O to a CH2OH group. And then if you've got a plane of symmetry that then forms with the sugar, you know that there's a sugar molecule that's symmetrical at least. So that is with threose or erythros. What about threose? Would threose show it? Okay, well, let's take a look. We have C double bond OH up here at the top, and then we have CH2OH down at the bottom. And we get an OH group here and an OH group here. Okay, so this is threose. Would threose have a plane of symmetry? Okay, well, we said that we can take NaBH4 and reduce the sugar down, and this converts CH2OH up at the top. CH2OH stays at the bottom. It was already there, right? The OH group stays there, the OH group stays there, and we need to figure out, is there a way that we can fold this sugar in half, either across or up and down? Up and down's fair game as well. So is there a way that we can fold the sugar to make it optically inactive or have a plane of symmetry? And the answer is no here. If I fold it here, well, the OH and the H line up and they don't really match, so that's not a plane of symmetry any longer. Well, if I fold it lengthwise, the OH and the H here, they don't really line up either, right? So that doesn't work either. So what we're going to see here is that this plane of symmetry, there isn't one. So there is no plane of symmetry. POS is what I like to use as an abbreviation. Because there's no plane of symmetry, that means that if I take 3-os and put it in the polarimeter, I'll get a read. Then when I add sodium borohydride to it and convert this to a COH or CH2OH group, well, that molecule in a polarimeter, it would give me optical activity. So that lets me know that this structure that I'm starting with, well, it's not symmetrical. There's something different about it. All the groups are not lining up, and I need to kind of figure out what groups are there, or what structures do I have to choose from where the groups don't really line up if I do get a optical read off of that polarimeter. So that's what this plane of symmetry is all about. We've kind of seen this before. You go back and you take a look at some stereochemistry chapter. Go back, take a look at the stereochemistry chapter. Take a look at these compounds that had more than one chiral carbon. And when you took a look at these compounds that had more than one chiral carbon, we talked about plane of symmetries there as well. And they had a very special term that they went by. And I would encourage you to maybe take a look at what that term they used to describe those molecules back in the day, because that could show up on the test. I'm not going to tell you the answer for it. I want you to dig for it, because this is part of the learning experience. So go through, take a look at the stereochemistry chapter, look at what happens when a molecule has more than one chiral carbon, and if there's a plane of symmetry involved, figure out what that structure is called. It does have a proper name that we use to go by. So look it up. Don't be surprised if you'll see it as a question on the test, because I'm telling you now, it could be. So hint, hint, hint. Don't let those free points basically take you away.